So we're very happy today to have Jared Speck with us. So Jared is a mathematician. He's on the faculty at Vanderbilt University. I should say he's also associated with the Initiative for Gravity, Waves, and Fluids at Vanderbilt. So kind of 3/4 of the BHI. And his research interests are in nonlinear partial differential equations, geometry, general relativity, fluid mechanics, and mathematical physics more generally. So today he's going to tell us about cosmological singularities in general relativity, the complete subcritical regime. Jared, you can take it away.
Thank you so much for the invitation. Thank you to Fabio as well. It's a real pleasure to be here. There's so many different things going on in relativity that I find to be exciting and fundamental and groundbreaking, from experimental results on, taking pictures of black holes and photon rings, multi-messenger astronomy. And in the theoretical world, we have proofs of the stability of black holes. 2 of them appeared in the last week, and these problems have been open for 18 years or more, depending on how you count. And the talk today will be about singularities in the context of cosmology. So this is not, strictly speaking, about the kind of singularity you would find inside of a black hole. It's more about the kind of singularity you would find at the beginning of time, a la the Big Bang. But there are some mathematical parallels between certain black hole singularities and the cosmological singularities that I'll talk about today. And I will mention those parallels again at the right moment. So let me start off with these really simple movies I made the other day, just to sort of set the stage for the kinds of collapse I'm going to be talking about. So this cube is supposed to be 3-dimensional space. Throughout the talk, space will be a d-dimensional torus, and I will say more about the particular number of spatial dimensions later, but d equals 3 spatial dimensions will be one of the dimensions I talk about. And I want to show you a qualitative movie about FLRW collapse. So this is a very simple picture. This is heading backwards in time towards the Big Bang, and everything collapses isotropically to a single point. And what you find mathematically when you study the curvature tensor of this solution to Einstein's equations, this FLRW solution, is that the curvature tensor blows up when the universe has shrunk to a point. So it's a real singularity in some sense. It's not some coordinate singularity, because what blows up, for example, is the Kretschmann invariant. The Kretschmann scalar blows up, and if an invariant quantity blows up, there's little hope to continue the solution. But I will say more about that later on. Okay, now in contrast, here's a different kind of collapse. So this is an example of what's called a Kasner solution, or later you'll hear about a generalized Kasner solution. I'll play the movie one more time. You also see shrinking in 2 directions, but an expansion in a 3rd direction. So it so happens for this particular solution, the expansion, and in fact, all the solutions I'll talk about today, the expansion is such that the volume of space goes to 0 as the collapse occurs. But in this anisotropic setting, you can have collapse in one direction and infinite expansion in other directions. Okay, and so one of the main themes of this talk is, first of all, to what extent are these explicit solutions to the equations stable? How these movies, simple movies, represent explicit solutions to the Einstein equations, which I will display in a few slides. And the basic mathematical question is, to what extent are these pictures dynamically stable? In particular, to what extent is the formation of a singularity, when all the way to the collapse, to what extent is that stable? And the compelling sub-question is, how is the stability of these solutions connected to the anisotropic behavior of the solutions? In particular, one of the things that will come out is that, and this is certainly not surprising at a qualitative level, it's simply harder to understand solutions when they're highly anisotropic. If you have collapse in one direction and expansion in another direction, as you might imagine, that makes the PDE analysis of the evolution problem much harder compared to the case of isotropic collapse. Okay, and as it turns out, there's sort of like a borderline threshold that one can identify, such that, sorry, I meant to share the other slides. There's a borderline threshold such that if you're above the threshold, you expect stability. And if you're below the threshold, there is high potential for wild instabilities to develop. Though nothing has been proved in the unstable regime, there's high potential for those instabilities to develop. And what we've done in this paper, by the way, we means my two collaborators, that's Igor Radnyansky at Princeton University and Greg Forno-Davlos. So he's about to start a tenure track position in Crete at Heraklion. Those are my two collaborators. What we've done is we've given a rigorous proof in the entire regime where we expect the stability of the collapse. And this is what we call the subcritical regime. This regime was not identified by us. It was identified by a series of other mathematicians and physicists, and I'll sort of explain to you how that numerology works. What we've done is we found a framework and a gauge that allows us to understand the complete regime where stability is expected. Okay, and there's some sort of interesting techniques that go into understanding the stable regime. Okay, so that's the background. And more specifically, here's what I'm studying. This is the Einstein equations in whatever number of spatial dimensions. Now here I have coupled to a simple massless scalar field. Okay. It's not rigorously been proved, but I believe that similar results will hold if you couple to Maxwell matter. What's unique or what's special about scalar field matter and Maxwell matter is that they have the same characteristics as the gravitational modes of the system. That is to say, all of these, all these matter models, the scalar field and the Maxwell model, they exhibit propagation along gravitational null cones. Okay, and that's sort of fundamental for the kinds of PDE analysis that we know how to do. If you go to a different matter model, say the fluid matter model, where you have motion along time-like characteristics, then all bets are off, and whatever the case may be of stability versus instability, there are lots of reasons to believe that qualitatively everything will be very different. The qualitative character of the flow will be very different if you introduce time-like matter. Okay. And if you're interested in the vacuum case, then yes, some of the results I will hold when the scalar field vanishes as well. So there are, a part of what we did applies to the vacuum case. And the precise details I'll share with you in a bit. Excuse me. So I am talking about the Cauchy problem on the D-dimensional torus, where D is the number of space dimensions. And so Cauchy problem means you have to prescribe initial data. So that would be the initial metric G, the initial second fundamental form, and the two pieces of scalar field initial data, basically the scalar field at, along the initial surface and its normal derivative, which is called phi1. And these tensors, of course, have to satisfy the constraints, but those are not important for this part of the talk, so I'm not going to go into the constraints right now. And we are going to consider initial conditions that are close in what's called the Sobolev norm, basically square integral norms, to the initial data of members of the famous Kasner family of solutions to the Einstein equations. Okay, so the pictures I showed you earlier at the beginning of the talk are pictures of Kasner solutions. And we're going to be considering initial data that are close to those solutions. And there will be two kinds of theorems. The first theorem concerns initial conditions with no symmetry whatsoever. And the second theorem is a stronger result under a polarized symmetry assumption on the initial conditions. Okay, so I'll come back to those specific details later when I state the result. And the fundamental theorem that one always leans on to get the discussion started for studying the evolution problem is the revered result of Choquet, Bruhat, and Garrosh, stating that the maximal globally hyperbolic development of the initial data exists. So M is the space-time manifold. It's going to have the topology of an interval of time cross TD. The G is the space-time metric that solves the equations, and phi is the scalar field. And the maximal globally hyperbolic development, in a nutshell, is the unique, up to isometry, largest possible solution, including the region itself, the space-time manifold itself. That is classically determined by the initial data. Okay, so this is the theorem that says this object that you would like to study exists, and it's a beautiful and important result, but it doesn't tell you anything really about the qualitative character of the maximal development. Okay, it doesn't really say, what happens at the boundary, for example. And so this talk is about exactly what happens at the boundary for initial conditions that are Kasner close. Okay. So the goal in particular is to understand stable space-like singularities. So there will be a space-like hypersurface. It will be in our coordinates, it will be a hypersurface of constant time. And along that hypersurface, the Kretschmann scalar will blow up. And we will think of this as a space-like singularity that develops along an entire space-like hypersurface. And it will be stable in the sense that it is insensitive to tiny perturbations in the initial data, where the notion of tiny is measured by one of these mathematical Sobolev norms. And if I have time at the end of the talk, I'll tell you a little bit about those norms. And because when you go to do the analysis, the choice of norms is really fundamental to everything. And the math problem, if you want, is for which open sets of initial data does the Kretschmann scalar blow up along a space-like hypersurface? We can interpret this as the dynamic stability of the Big Bang. Okay. And so why am I interested in this problem besides the fact that it's an interesting math problem? Well, the Hawking-Penrose singularity theorems, which I'll review in the coming slides, they tell you something about perturbations of Kasner. They tell you something interesting. They tell you that there's some kind of incompleteness, but they don't tell you the source of incompleteness. And so one of the questions one might want to entertain is, what's actually going wrong in the Hawking-Penrose theorem? What is the nature of the incompleteness? Because there are multiple kinds of incompleteness that are known can in principle occur in solutions. Of course, we're driven by the existence of explicit solutions like the isotropic FLRW solution in the Kasner family. We want to know to what extent are these explicit solutions that you can write down on a piece of paper, to what extent are they representative of the actual dynamics you might encounter in Mother Nature if you're in one of these regimes. And as I mentioned earlier, there's a lot of heuristics in the physics literature, and a lot of inspiring heuristics that it ends up being morally correct. So I'll review those and back of the envelope calculations later in the talk. But at the end of the day, sort of what should happen has been identified from multiple angles. And it turns out there's quite a gap in mathematical difficulty between identifying what should happen and actually showing that it does happen. And so I'll explain some of those difficulties later in the talk. And then, of course, there's a huge body of work on numerical simulations involving singularities. Okay, and I unfortunately don't know much about numerical analysis. So whenever I see a talk on singularity formation from a numerical person, I really have very little intuition about to what extent I can attribute this to a real singularity, or to what extent limitations in the numerical scheme might be afflicting the dynamics. So basically, we want to put a theoretical underpinning to some of the simulations that have been done. And before we did our work outside of symmetry, there were other works, including some rigorous results under symmetry assumptions and under the assumption that the initial data are analytic. And it's well known that if you assume symmetry, that can be very misleading. Assuming symmetry is basically turning off some modes of interaction. And so we were also motivated to sort of remove these symmetry assumptions to the extent possible. And then certainly the breakthrough of DeFermos-Luc from a few years ago about the stability of a little piece of the Cauchy horizon inside of the black hole was also very motivating, because there in this work, they showed that a different kind of geodesic incompleteness is stable, namely the incompleteness attributed to the formation of a Cauchy horizon. And so what we wanted to understand was, what is the nature of incompleteness for near Kasner solutions? And of course, the intuition is that, you cross your fingers and hope that the incompleteness for near Kasner should be for exactly the same reasons as for Kasner itself, namely curvature blow up rather than some Cauchy horizon or some other monster. Okay, so back to these generalized Kasner solutions. This is our terminology. You don't really see this in the literature. We call it generalized Kasner because Kasner usually refers to vacuum solutions. And here we're allowing, for example, for the presence of a scalar field. So this is the Kasner metric. It's a family of metrics. So these QIs are constants. They have to live in the interval -1, 1. And B is some constant bigger than or equal to 0, representing the initial amplitude of the scalar field. And here's a good point for me to emphasize that we're starting the dynamics at t equals 1, so that's like the present state, and we're solving backwards in time towards t equals 0. So that's like solving towards the past where, maybe the Big Bang occurred. And in order for this metric, G Kasner, to satisfy the Einstein equations, the QIs cannot be chosen freely. They have to satisfy what are called the Kasner constraints. They have to add up to 1. This is more like a gauge choice for your time coordinate. And then the big one is that their squares have to add up to 1 minus b squared, where b is the scalar field amplitude. And this is essentially coming from the Hamiltonian constraint. Okay, so or these two constraints together, they actually, especially in a vacuum, they place restrictions on the kinds of solutions that you're even allowed to study consistent with the Einstein flow. And this is one of the things that makes the problem very difficult in low dimensions, is that these constraints. And I'll say more about that in a little bit. And for all of these Kasner solutions, except for a special case where, let's say, b is 0 and one of the exponents or one of the q's is equal to 1 and all the rest are 0, except for that very special case, which is a flat case, the Kretschmann scalar blows up at time 0. So all of these Kasner solutions, except the exceptional one, all of these solutions exhibit curvature blow up at time 0. In fact, you can compute explicitly the blow up rate in terms of the Kasner exponents. And this constant is some function of the q's, some polynomial or rational function of the q's. And the blow up rate is basically t to the minus 4. Okay, and it ends up being really important for the talk, or let's say for the analysis, knowing the precise blow up rates of various tensors that do end up forming a singularity. So at the end of the day, the perturbed solutions that we study will also exhibit Kretschmann scalar blow up at the same rate for a slightly different C. Okay. And so this is what we mean by Big Bang singularity at t equals 0, essentially, for these solutions. Okay. So let me now revisit the Hawking theorem that I mentioned earlier. It comes in many different flavors, of course. So this one is specialized to the case where the space manifold is the d-dimensional torus. Okay, so let mg phi be the maximal globally hyperbolic development of the initial data, which thanks to Gorosh and Choquet-Bruhat, we know this object exists. And assume that the trace of k is strictly negative along sigma 1, along the initial Cauchy hypersurface. Okay, and by the way, this is satisfied for the Kasner solutions. For the Kasner solutions, this trace is always equal to -1 everywhere along sigma 1. And a conclusion is that no path-directed time-like geodesic that emanates from sigma 1 and goes backwards in time can be longer than some computable constant C prime. So for some reason, not told to us by Hawking's theorem, after C prime amount of affine parameter time, you crash into some kind of incompleteness occurs. And of course, we would really like to know what's the source of the incompleteness. And not only does Hawking's theorem apply to Kasner itself, trace chi is -1, it manifestly applies to perturbations, because if you slightly perturb the initial data, you'll be slightly perturbing -1, and whatever you get, it's going to be strictly negative all along the initial Cauchy hypersurface. So we already know from Hawking that for initial data near Kasner, there will be some kind of geodesic incompleteness. What we don't know is what's going on. And this is what we want to know. Why are the time-like geodesics incomplete? Okay, we know it for Kasner, but what about perturbations? And here are two sources of incompleteness. So there's the curvature blow-up, or there's also something called a crushing singularity, and I'll say what that is later in the talk. A crushing singularity. It's basically blow-up of the second fundamental form. And we know that there's Cauchy horizon formation inside of Kerr black holes, and that this is stable. This is the Fermat's loop result. And so we want to sort between these two possibilities, or there could be in principle other monsters. Okay. So here's the first statement of our main result. So this is the subcriticality condition, where the word subcritical appeared in the title of the talk. You look at the Kasner exponents, okay, and you form these combinations, qi plus qj minus qb, and where these are all added up. And then you look at the maximum value that this takes on as you allow I, j, and b to vary over all of the spatial indices. And you can assume that I is less than j. Let me not get into that technical assumption. It's not such a big deal. If this max is less than 1, then this is the condition that we will prove determines the stability of the Kasner Big Bang. So this is it. This is the sharp criterion that defines what we mean by subcritical regime. And let me return to the issue of low dimensions and the Hamiltonian constraint. If you go to the vacuum, case, so you put the scalar field equal to 0, and you try to satisfy this in the vacuum, you try to find some Kasner exponents that satisfy this in the vacuum. Of course, they also have to satisfy the Kasner constraints, those two algebraic constraints. Then you can satisfy this inequality if and only if you're in 10 or more spatial dimensions. And so the heuristics for this calculation essentially was carried out in the 1980s by Desmarais, Hinault, and Spindle. They had this beautiful paper entitled something like Non-Oscillatory Kaluza-Klein Cosmologies. And they were the ones to sort of really, they were not the first to investigate these kinds of subcriticality conditions, but they were the first to nail it down in the vacuum, and they were the first to understand that this can only be done in the vacuum case when D is at least 10. So in particular, you can't do this in a vacuum in 3 space dimensions. There are no such Kasner solutions that satisfy this subcriticality condition. Okay. And once again, I want to point out that the Fermos-Luke result shows you that you have the stability of the Kerr-Cauchy horizon. It's also dynamically stable. Why am I harping on this? Because I think there's really a key takeaway from these two theorems. In relativity, there's distinct kinds of incompleteness that can occur in different solution regimes, which are now known to be stable. So, the theory is already pretty rich as far as what kinds of geodesic incompleteness is known to be stable outside of symmetry. And I also think it's important to keep an open mind about, in principle, other stable pathologies could dynamically develop. So this is not something that I've read very much about. I don't see it discussed a lot, but in principle, other things can go wrong in relativity, right? There can be other kinds of singularities. And, it's fair to say that nothing is rigorously understood, maybe not even qualitatively, heuristically understood, but I do think one should be open-minded and maybe, anticipate we might not be able to make a definitive large data statement about all possible bad things that can happen in relativity, even generically. I think that we're far away from ever being able to say that. Okay, so where do these back of the envelope calculations come from, and where does all of this insight about subcriticality and so forth come from? Well, it certainly can be traced back to the famous BKL papers. There are various papers that have various permutations of BK and L in them. But in all of their works, there is the following philosophy that's adopted. So these are physics papers from the late 60s and 70s. So this is what a BKL metric is by definition. It's got the trivial time part, and then it looks like a Kasner solution. And if you can put a scalar field there if you'd like. Except the exponents Q and the scalar field amplitude are assumed to be allowed to depend on the space variable X. So X is the element of the d-dimensional torus, if you want. And you still assume that the Kasner constraints are satisfied. So the Q's add up to 1 and their squares add up to 1 minus bx squared. And as I've highlighted, in 3 space dimensions, the subcriticality condition fails. The condition that we put on the Kasner exponents, it's not possible to satisfy that in 3 space dimensions. And part of the BKL story, so it's actually very difficult to say what is the BKL picture, or what are the BKL conjectures. They have multiple elements to them. But certainly one crucial aspect of the story is that let's say in 3 space dimensions where subcriticality is impossible, if you get close to what is hopefully a space-like singularity, hopefully if you like space-like singularities, most solutions should oscillate violently in time. Okay, and this is this is what we believe is connected fundamentally to the fact that you can't have a subcritical configuration of Qs in 3 space dimensions. It should, we believe, though there's nothing rigorous that's been proved, there should be violent oscillations in time that where the dynamics essentially looks radically different than the Kasner and FLRW dynamics. Okay. This is the expectation that coming from the BKL works. And how did they do it? Well, they took this ansatz for the metric. They assumed that you have a metric that looks like this, and they plugged it into Einstein's equations. And one thing you'll find is that these BKL metrics are typically not solutions. These do not solve the Einstein equations. Okay. Nonetheless, through their back of the envelope arguments, they argued that this should be a good approximation to an actual solution in certain regimes of time. So these are the BKL epochs, if you want, where for certain lengths of time, a metric like this with some X dependence should somehow approximate an honest to God solution. So in other words, they tried to divide the dynamics up into little time scales where each time scale is described by one of these BKL metrics. And then as you transition from one epoch to another, there was sort of a numerology for how the Qs can change, or if you want, how you jump back and forth between different epochs. And the numerology is very fascinating, very important, and a lot of papers have been written on this. But to this day, I'm not aware of any rigorous result that sort of justifies this picture in an oscillatory setting if there's honest to God spatial dependence in the solution. So I don't think this bouncing between epochs has been really justified all the way to a singularity for any solution except those that depend only on T. Okay, and so I'll say a little bit more about that later. Okay, now despite all of this, there's some very interesting recent work by Forner-Davlos and Luke, where they construct a large family of solutions to Einstein equations that look like this. This is Einstein vacuum equations in 3 dimensions, where B is 0, and they look like this. And the solutions that they constructed do not oscillate. They do not exhibit violent bounces between different Kasner epochs. In fact, the solutions that they construct are essentially asymptotic to these kinds of metrics right here. And why do I especially think this paper is important? Because they did this not just for like 1 or 2 pieces of initial data. They found 3 functional degrees of freedom in the Einstein vacuum initial data, where you can construct these non-oscillatory solutions. So 3 out of 4, because there's 4 fundamental degrees of freedom in the Cauchy problem for the vacuum equations in 3D. So basically, the conjecture at so I would say the correct conjecture at this point is that the missing degree of freedom that's not accounted for in the Forner-Davlos-Luke theorem, the missing degree of freedom is exactly the one that should create these violent oscillations. Right? And so, I think one day there's hope that one can say something rigorous about turning on this additional degree of freedom and maybe saying something about these oscillations. But that is a beautiful open math problem right now, to say something about this other degree of freedom. Okay. Now, back to this subcriticality condition. So I talked about the violent oscillations. Now, what about the monotonic regime? So the first pair to identify the possibility of a different regime where monotonicity kicks in were the pair B and K, Belinsky and Klatnikov. And this was for they understood this for the Einstein scalar field model. They understood that if you put a scalar field into the picture, then thanks to the scalar field amplitude B, you can put yourself into a regime where these exponents satisfy this, even in 3 space dimensions. And a lot of people followed up on this, the famous physicist Barrow, and the paper by Desmarais, Hainaut, and Spindle that I mentioned earlier, and mathematicians Anderson and Rendell, and then a math physics team, Damour, Hainaut, Rendell, and Weaver. They all sort of identify conditions that at the end of the day can be translated into this. This in their works, this was the condition that heuristically they decided based on these back of the envelope calculations. And in some cases, there are some rigorous results behind this, that this condition should be the one that stabilizes the flow. This should be the one that leads to dynamic stability. And later in the talk, I will try to say a little bit of something about how this connects to the the connection between this condition and the analysis that one does to prove stability. In the new gauge we used, this condition sort of jumps off the page at you, the significance of it. Okay, and for all of these works, the significance of this condition is that if you go to the heuristics and you look at the different terms in Einstein's equations and whatever gauge you're using, these heuristics suggest that the Einstein equations, that the flow should be dominated by time derivative terms. That, this is called asymptotically velocity term dominated behavior in the literature. The basic hope, if you believe in the heuristics, is that you can sort of treat the Einstein equations like differential equations where the space derivatives don't really matter that much, right? Don't really matter that much. That's the hope. And the rigorous results that came out of these works, so for example, by rigorous, I mean Anderson, Rendell, and Damore, Hendo, Rendell, and Weaver, the rigorous results that came out of the heuristics among this batch of works concerned justifying this behavior when the solutions are spatially analytic. So when you can do a full power series expansion in the X variable. These works sort of justified the connection between this stability condition and the dynamic stability of the flow. And while that's a beautiful and important set of works, there are good physical reasons for wanting to go beyond the analytic class. For example, in analytic class, you kind of, in a weird way, violate finite speed of propagation because analytic solutions are sort of instant, uniquely determined by their Taylor expansion at a point, which sort of, violates wanting to see finite speed of propagation. Okay. And other things came out of these works as well. If you go to a symmetry class, then a similar batch of heuristic ideas suggests that stability might hold for even more Qs, sort of outside of this regime within symmetry. And one of the results that we proved exactly concerns exiting this regime when you have polarized symmetry. Okay, and I'll say more about that in a bit. Okay, I already mentioned that there's a large group of work on numerical, on singularity formation coming from different angles, like numerical relativity, works in symmetry, and there's work on the linear analysis and construction of singular solutions as opposed to stability. And there have been a few investigations of the oscillatory regime, but there's not very much has been done in the oscillatory regime. The big result here, I would say, would be Hans Ringström's proof that Misner's mixed master solutions are real and stable effect within the Bianchi-9 symmetry class. This is my favorite result as far as oscillatory solutions go. But this result is in Bianchi-9 symmetry, and in particular, that means there's no space dependence. It's basically a complicated system of ODEs that exhibits the oscillatory behavior. So it's a great open math problem. Try to find an oscillatory singularity where there's honest to God X dependence. Okay. All right, so here is the theorem that we proved. It comes in several flavors. So assume the subcriticality condition. This is part one. Then the Kasner solution, which looks like this, is dynamically stable as a solution to the Einstein scalar field system under Sobolev class perturbations of the initial data. So this refers to the norm. These are the standard square integral type norms that are known to be fundamental for the mathematical well-posedness of the Einstein equations. So at the end of the day, they're kind of the natural mathematical norms that one works with in the rigorous theory of the Cauchy problem. So we assume the initial data are given on at time 1, and we construct these constant mean curvature coordinates. Okay, and constant mean curvature ends up being really important for the analysis in ways that I want to make clear. So what do I mean by constant mean curvature? I mean that this at each fixed time. So if you fix t, let's call the constant time hypersurface sigma t. If you look at the trace of the second fundamental form of that constant time hypersurface, we parameterize space-time so that everywhere along that hypersurface, the trace is -1/t. And this is exactly what is satisfied by the Kasner and FLRW solutions in their natural coordinate systems. So this is basically the same same behavior that you're seeing for the Kasner solutions. Okay. And here are two statements from the two quantitative statements from the theorem. First of all, the Kretschmann scalar for the perturbed solutions also blows up like t⁻⁴. So this is the curvature singularity, if you want. This is Big Bang. Next, the volume form of the space-time metric G, its coefficient goes to 0 as t goes to 0. So this is basically the volume of space collapsing, just like I showed you in both of those movies at the beginning. Okay. Now I want to say something about one of the components of the metric, the lapse, which is fundamental for the way that we set up the problem. So the definition of the lapse is basically it's the length of the gradient of the time function t, except you take the reciprocal and you put it in absolute value because dt is time-like. Okay. So this is one of the components of the metric that you have to solve for. And in this gauge, it's well known to mathematicians who work in this area that the lapse n solves an elliptic partial differential equation. So even though the fundamental dynamics of the Einstein equation are hyperbolic, our gauge involves an elliptic partial differential equation. And what's, depending on your view, good or bad about elliptic partial differential equations is that such gauges involve an infinite speed of propagation. Basically, to solve for the lapse, you have to solve across space at each instant, okay? And so that's kind of it's not really a violation of relativity because at the end of the day, it's just a coordinate choice. But this ends up being philosophically really important for what we're trying to do because this is essential for synchronizing the singularity. You know, our statement is that the Kretschmann scalar blows up everywhere along the hypersurface corresponding to t = 0. And in a hyperbolic problem, a pure wave problem, it's impossible to do this because if you have 2 points that are far separated in space, and each one is about to form a singularity, or there's about to be a singularity near each point. In general, if you're using finite speed of propagation type gauges, you have no way to synchronize the two blow-up points and to say that they both blow up at time 0. The only way to synchronize is to set up a gauge where you're sort of solving across space at each instant in time. And so that's why that's actually why we need the infinite speed of propagation gauge in the problem, is simply to synchronize the singularity. Now I should mention that even, we didn't put it in this paper, it's in one of our earlier papers. If it's preferable, for example, for numerical simulations to replace this elliptic partial differential equation with a parabolic heat flow type differential equation, that can be done as well. So there's this sort of a parallel approach to proving all of these results, where instead of using an elliptic PDE for the lapse, you use a parabolic PDE. And essentially, the lapse would solve the heat equation. And so that, it's my understanding that that might be better in some numerical simulations. That computers are that parabolic flows are easier to implement numerically in some cases compared to elliptic equations. Okay, now here comes the second result. This one's in symmetry. This one concerns 3 spatial dimensions. Okay, and so remember, 3 spatial dimensions in a vacuum. It's guaranteed that this condition fails. That was the result from the 80s by the trio. This subcriticality condition definitely fails. However, if you assume that the initial conditions are polarized, you have 1 symmetric perturbations. And it's very easy to say what this means. Okay, it means that in a certain coordinate system, the 1, 3, and 2, 3 components of the spatial metric are 0 for all time. Okay, that's the polarization part. And the U of 1 symmetry part is that there's no dependence on the third spatial coordinate, x3, if you want. So this is polarized U of 1 symmetric. Then, in this symmetry class, all Kasner Big Bangs are dynamically stable. You simply do not need this subcriticality condition if you go to polarized U of 1 symmetry. Okay, and actually our proof sort of really shows you what's going on and why we can say a lot more within the symmetry class. Okay, there's a nice circle of ideas that sort of connects all of these things. Okay, and this theorem covers the entire regime where the back of the envelope calculations have been worked out. So any future results that concerns stability or instability of other solutions will be outside of the regime where the heuristics have been worked out. Okay. And I have worked on similar problems before. So with Rodnyansky, we did D equals 3. That was one of our first papers. And with all the Kasner exponents to be equal to each other, this is stability of FLRW Big Bang. And then we had a follow-up paper where we had to do, this is a follow-up vacuum paper with at least 39 spatial dimensions, which allowed us to study, in 39 or more spatial dimensions, you can find Kasner exponents where their absolute value, all of them, all the Kasner exponents are less than 1/6 in absolute value, which clearly falls within this regime. But in any case, we had sort of like a much worse gauge for in this follow-up paper. So this is a big jump over what we have done earlier. Okay, let me say something about crushing singularities because I mentioned that terminology at the beginning of the talk. So mathematicians, being what they are, you know, they have the dream that maybe they can solve past the singularity if they simply weaken the notion of what it means to be a solution. Okay, and for example, the whole theory of weak solutions in the mathematical context of shock waves is about realizing that dream in fluid mechanics. So in relativity, in principle, one can try to do the same thing. You can try to set up what's called a weak notion of the flow, and maybe just because the curvature blows up, perhaps, you know, maybe you can still solve past the singularity. No, there's hope. Okay. However, all of the methods we know for trying to weakly continue the solution would require that the space-time integral up to the singularity of the Christoffel symbols squared, so this is like one of these energy norms, should be finite. And if you take a look at what's going on for the solutions that we constructed, so the second fundamental form, if you square it, it's going to blow up like t to the minus 2, and the volume form is going to go to 0 like t. So if you put the two together, it's like t to the minus 2 and t, you get 1 over t. And if you integrate that in time, you integrate 1 over t, you get log t. And at the t equals 0, you get log 0. So you get something infinite. So that means that these singularities that we constructed, they sort of lie outside of the domain where one can hope to weakly continue the solution. So for us, this is as severe as a singularity as it gets. And we wouldn't know how to continue past it in principle. Okay, so how am I doing on time? It looks like it's been about 45 minutes.
Yeah, you have 15 more list. Actually, you have almost 20 minutes from now.
So would it be okay if maybe I talk for 10 more minutes and then that would leave about 10 minutes for us to talk about whatever?
Yeah.
Okay. Feel free to remind me if I lose track of time. Okay. So now a little bit more about the gauge. So we used a zero shift decomposition of the space-time metric. So we decompose it into the dt squared part, which has a coefficient of minus n squared. N is this lapse. And then there's the spatial metric, non-bold g, that lives on each sigma t. And for such a metric, you can talk about its future directed unit normal. We call that E0. Okay, this is all sort of standard so far. And you can talk about the second fundamental form of sigma t, and this is our normalization, our definition of the second fundamental form, where these di's and dj's are coordinate partial derivatives. Okay, and one can compute that in this gauge, the coordinate component, kij, is equal to minus a half the E naught derivative of gij. So I'm harping on this to point out the notation that's being used. Here, the lowercase Latin indices represent indices with respect to the coordinates, and E naught applied to gij, this means the derivative of this coordinate component Gij in the E naught direction. So this is an E naught directional derivative. This might not be familiar notation to you, but this is how some people in differential geometry choose to express these things. And I already mentioned that we used CMC's gauge, where the trace K is -1/t. And this gives you an elliptic PDE. And here's the new ingredient where we really get some sharp structure. Instead of working purely in coordinates, we complement E0 with the Fermi-Walker propagated orthonormal spatial frame. So it's quite easy to construct by the famous Graham-Schmidt algorithm, a spatial orthonormal frame at time 0. And then we propagate it. So this basically says that so here we have these D spatial frame vectors, and the Latin index, the big Latin index, capital I, is a label for the frame, so it's not a tensor index, it's just a label. And the lowercase index, little I, is a component of this vector field with respect to this coordinate system. And again, this represents the E naught derivative of this scalar function EII in the E naught direction. And using Einstein summation convention over the frame label indices as well, okay? And it's not, maybe for those of you who have worked a lot with Fermi-Walker, it may not be immediately apparent to you that this is Fermi-Walker transport. This is in fact equivalent to the usual Fermi-Walker transport equation within this gauge, okay? So this is the, if you want, this is the way that we can propagate a spatial frame. Okay, so this is just a simple transport equation for some frame vectors. Okay, and this gives you a spatial frame for all time. Okay, and here's the philosophy of the proof of the PDE analysis. We recast Einstein's equations as an elliptic hyperbolic partial differential equation system. So the hyperbolic part comes from the Einstein part. The elliptic part is simply from the from our choice of CMC foliations, where you have this elliptic PDE for the lapse. And we reformulate this as a system for the frame component functions. So for all of the components of the EI frame with respect to these coordinates. Okay, and here's what the unknowns are. The lapse, this is a scalar. The spatial connection coefficients, this is where we see the magical cancellations that I haven't shown yet. So the connection coefficients of the frame defined by, you take the covariance derivative of EJ in the EI direction and you inner product it with EB. That's our definition of gamma IJB. So these are not really tensor indices, these are like frame label indices. You can think of them as scalar functions because these are just frame labels. So we think of these as unknowns in the problem that we have to solve for, and the components of tensors with respect to the orthonormal spatial frame. So instead of solving for the coordinate components, KCD, we solve for their frame components. And finally, at the end of the day, we do need some very weak information about the components of the frame with respect to the space coordinates as well. But we only need very weak information about this. So these are all the unknowns in the problem, at least in the vacuum. And if you have a scalar field, there's also the normal derivative of the scalar field and the derivative of the scalar field in the space frame directions. So basically, these are the unknowns in the PDE system that we study. Okay, and if you want, the goal would be, you know, more or less to derive estimates for the system. And in the vacuum case, here is what the Einstein equations look like in this gauge. Okay, you have evolution equations for the frame components of the second fundamental form, and on the right-hand side, you have first derivatives of the connection coefficients and the connection coefficients themselves. So if you want, the spatial Ricci curvature is hiding on the right-hand side. And then we have an evolution equation that connects, or that tells you how the connection coefficients evolve in terms of the second fundamental form and its derivatives. Then we have an elliptic PDE for the lapse. So it might not be apparent, but this EC, remember ECs, so we're using Einstein summation convention, and the ECs are an orthonormal spatial frame. So this is actually, this term on the left for the lapse, this is basically the Laplacian up to lower order terms. This is the elliptic PDE for the lapse. And then these two constraint equations do actually enter into the analysis. And one of the basic new observations that we had is that this system is actually mathematically well posed. So this was a new observation, simply that you can actually formulate the Einstein equations in this fashion and get a basic well-posedness theory that allows you to prove, for example, local existence in time. Okay, it doesn't tell you anything about the global structure of solutions, but it is important that solutions to Einstein's equations in this gauge are well-posed in the standard Sobolev spaces. Okay, now let me highlight, I feel I'm about to, I'm getting low on time, so I won't display all the slides and I won't talk about the analysis. Let me just highlight 3 features of the gauge that may be of interest to you. First, I've already mentioned, which is the elliptic PDE synchronizes the singularity. The second one concerns the structure coefficients of the frame. And this is where we see the miracles. This is where we see the sharp structure that I think, this is what enables us to understand the full regime. What are the structure coefficients? SIJB. So these are scalars, the way we think of them. By definition, you take the Lie bracket of EI with EJ, and then you inner product it with EB. And you can, by the usual torsion-free property of the connection, you can re-express this if you want in terms of the connection coefficients of the frame. Okay, and so you can think that these SIJBs are anti-symmetric combinations of the connection coefficients. Okay, and here is the miracle. This is the diagonal structure. This is the diagonal structure. If you write down an evolution equation for the structure coefficients, what you find is that up to PDE error terms, which I certainly will not talk about here, the structure coefficients solve a diagonal system. And moreover, the main coefficients are exactly the coefficients that come from the subcriticality condition. Okay, if you write down the time derivative of the structure coefficient and you use the Einstein equations, you find that the main coefficient in front of the main linear term in the structure coefficient evolution equation, it has a diagonal structure, and the subcriticality combination jumps right off the page at you. And so if not for these error terms, you could immediately integrate this. You can immediately integrate this in time and figure out exactly what the behavior of the structure coefficients is. And by assumption, if you're in the subcritical regime, this coefficient will be less than 1, right? And so in particular, if you take them, if you run this machinery and you sort of treat the PDE error terms in a way that the actual argument goes through what's called a bootstrap process. But at the end of the day, what comes out of it is that if you perturb the initial data of Kasner, you will get structure coefficients that behave almost the same as they do in Kasner, where the Q's can change a little bit. So this epsilon is like a little bit of error room that you allow yourself because you're doing PDE error estimates, and epsilon is going to be small. And if your subcriticality condition is such that these 3 Q's for the Kasner solution are always less than 1, then if you make a small error, the perturbed solution will be such that this is less than 1 as well. And so what this tells you at the end, our setup gives you that the structure coefficients, they're no more singular than t to the minus q, where q is strictly less than 1. Strictly less than 1. And what's so magical about q being less than 1? Guess what happens if you integrate this in time? If you integrate t to the minus q in time, all the way down to q equals, let's say from q goes from 0 to 1. If you integrate from 0 to 1, t to the minus q, and q is not too big. So strictly, if this is strictly less singular than 1 over t, you will get a finite integral. And so that is the crucial point for the stability of the flow. It jumps right out of you from this equation satisfied by the structure coefficients. The integrability of t to the minus q when q is less than 1 is what gives you the stability when you go to do the difficult math analysis. Okay. And so looking at the clock, I'm basically out of time. So let me skip any discussion of the proof and just jump ahead a little bit to reiterate what I said towards the beginning of the talk. Questions that have not been resolved at all that I think are very interesting. What happens in the presence of time-like matter? Like I said, the setup tells you something about vacuum, it tells you something about scalar field, and it tells you something about in principle, I think it can be done for Maxwell equations as well, but it doesn't tell you anything, for example, for the Einstein-Euler system. When you have a perfect fluid, what happens? Totally unknown. And finally, in principle, I think it's a really worthy avenue of investigation. What can you hope to prove outside of the monotonic regime? Suppose you leave a regime where this subcriticality condition, where subcriticality meaning this is less than 1. Suppose you go into a regime where this is bigger than 1 now. What can you even hope to prove? What should be true? I think basically every interesting math problem is open. And I would argue that the heuristics are not even well understood. So I think there's even a lot of room to contribute at the level of heuristics. Okay, I'll go ahead and stop there and open up the floor for whatever kind of questions are out there.
All right. Yes, thank you. Thanks, Jared. So we have some time for questions. So you can either raise your hand or just unmute yourself if you have a question.
Achilles, are you going to moderate it?
If there is a need for it, but
okay, yeah.
at the
So
moment,
I saw hands go up and now down.
Oh, I saw some clapping. So
okay.
Yeah, I saw some clapping. But at the moment, anyone can unmute himself and ask a question.
Hi, Jared.
Hi, Watson.
Could you speak a little bit more about the structure that you mentioned at the end, which was responsible for, or what you?
Yeah. So let me let's see, the diagonal structure.
Yeah.
Yeah. So maybe it would be useful for me to say to sort of explain why we can handle the polarized U of 1 symmetric case without restriction on the Kasner exponents. Maybe that will be telling. So here's what's happened. Let's go to symmetry class now. Let's go to polarized U of 1 symmetry. And here's the magic that happens in that symmetry class. Because as an artifact of symmetry, all of the structure coefficients that have 3 distinct indices. So for example, S1, 2, 3, 3 distinct indices, 1, 2, 3. Because of symmetry, those vanish. That's an artifact of symmetry. So in that symmetry class, you are guaranteed that all structure coefficients are 0, except for the case where 2 of the indices agree. One of the 2 of the I, J, and B have to agree with each other. Now let's go to this combination. 2 of these agree. That means one of them will cancel, or 2 of them will cancel. If 2 of these are the same, you will have some cancellation. Okay, and therefore you're basically left with a single Q. After the cancellation, you're left with a single Q, and that Q is guaranteed to be less than 1 in magnitude by the Kasner constraints. So within that symmetry class, you're guaranteed that the S's, irrespective of any subcriticality condition, the structure coefficients will behave like T to the minus Q, where Q is less than 1, so you have integrability. Now let's go back to the Einstein equations in our gauge and look at these quadratic terms, gamma times gamma. So these are the terms that have the most potential to be singular. You'll have to take my word for it. This is one of the things that comes out of the back of the envelope calculations done by the physicists. Gamma times gamma. Well, what you can do is there's the famous causal identity. You can always express connection coefficients gamma as linear combinations of structure coefficients. So you might as well think that instead of gamma times gamma, you have like S times S, because where S is a structure coefficient, because the causal identity allows you to always express gamma in terms of S. Okay, so now let's see what are the most singular terms in the equations. What does K look like? K should look like 1 over T, because that's what you see in Kasner. What about dtk? So that's the left-hand side. If K is like 1 over T, then dtk is like 1 over T squared. So you should think that the left-hand side has the strength of 1 over T squared. Also, the main term on the right-hand side, this K over T, also has the strength of 1 over T squared. So it's 1 over T squared, 1 over T squared. Now, what about these terms, the gamma times gammas? Well, I just told you to think of them as like S times S. And what have I told you about S in the regime that we understand? It's strictly less singular than 1 over T. S is less singular than 1 over T. It's like T to the Q or T to the minus Q, where Q is less than 1. So these terms, these gamma times the gamma current terms, are strictly less singular than t to the minus 2. Strictly less singular. And so that's how you justify the claim that the time derivative terms dominate. That's how you sort of are able to treat the spatial derivative terms as represented by the connection coefficients as being less singular than the time derivative terms. That's how we implement this into the PDE analysis.
So the U1 is huge, right?
I'm sorry, what's huge? U of 1?
So the assumption, can you go back to the Q exponents, like what this?
For U of 1 symmetry, there's no assumption whatsoever. All Kasner Big Bangs. It doesn't matter. This condition doesn't enter into the analysis at all.
Yeah. Okay. So yeah. Okay. So the U1 just kills that assumption.
It kills all S's where you have 3 distinct indices. Those
Gotcha.
such S's are guaranteed to be 0 by the symmetry assumption. That
Gotcha.
means that when
Okay.
you go to study this diagonal system, the only monster that could be an obstruction to stability, which is the monster where you have 3 distinct indices where they add up to something bigger than 1, that monster is guaranteed to be absent.
Gotcha.
So certain structure coefficients vanish by symmetry, and then the ones that do remain are guaranteed to be have this integrability property. So only the good structure coefficients survive. And this
Gotcha.
sort of tells you, this is, what determines whether you're in the stable regime or the regime where things can go wild is essentially the structure coefficients of a frame. That's one way to think about it.
Nice, but so if I understand correctly, that actually the term that could be bad is actually good, and so does that not give you leeway to maybe do something, maybe deal with those 3 indices somehow a bit more pathological than what you end up having in this setting? Or is that not really, is that just
if you break the symmetry, then you can have situations where all structure coefficients are non-zero, and you have a coefficient that's larger than 1. That's possible to do away from symmetry. And in that case, you will in principle be able to prove a bound like this for a short time, but here Q can be bigger than 1. If Q can be bigger than 1, if you go back and you plug that into Einstein's equations, that's telling you that the dominant effect is actually coming from, in principle, from those structure coefficients. So that's the opposite of a time derivative dominated regime. That's a regime where the space derivative terms take over. And I'm not aware of any rigorous result on that regime. But on the other hand, the transition the heuristic results in the literature on bouncing between different Kasner box, those results are predicated on assuming that you do enter into a regime where these connection coefficients do become dominant and push you into another Kasner epoch.
Oh, okay.
So, it's actually, I think, and probably you can see this numerically for short time, not all the way to the singularity, but probably numerically, let's say for the mixed master solutions, you can actually see that the space derivative terms do become dominant and they do push you into a new regime.
I see. Okay. Nice. Thank you.
Sure.
Yeah, thanks. Are there any other questions?
Can I ask? Hi, Jared. Thanks for the talk. Yeah, nice to see you too. Do you have any? You mentioned at the end the Einstein Euler equations. Have there been any kind of heuristics or numerics or ideas there that give you some expectation of what could happen?
Great question. The answer is yes. Hans Ringstrom has papers in Bianchi 9 symmetry.
Yeah.
In symmetry, he showed that the dynamics are oscillatory. They're definitively oscillatory, except if the speed of sound is equal to the speed of light for, that special equation of state.
Yeah.
For all of the other equations of state, the symmetric solutions exhibit oscillatory behavior. The oscillations are described in the context of dynamical systems. What that means is Ringstrom formulates the Einstein equations in symmetry as a system of ordinary differential equations and shows that you have, as you head towards the singularity, his proof showed that you have at least 3 distinct limit points.
Mm-hmm. Yeah.
So that's very different than the kind of monotonic collapse that you see in
Yeah.
FW. So already the symmetric solutions are behaving wildly different. And that's for Einstein Euler. He also did it for Einstein vacuum. And the heuristics behind that's nothing other than Misner's famous mixed master solutions.
Mhm.
You know, how can you implement Bianchi-9 symmetry? You take the space manifold to be S3, and you there on S3 there's a global frame, and you can
Yeah.
look at the coefficients of that frame as functions of time and plug them into Einstein's equations, and you get a coupled system of differential equations for those three coefficients. And you study the dynamics, and you see that the ODE system can exhibit oscillations between different points on what's called a Kasner circle, where the circle sort of captures the constraints.
Right, I see.
So the picture is definitively different qualitatively for Einstein-Euler.
Yeah, yeah, I see. Thanks.
Okay, we're a little over time, but we can have the last question from Shahar.
Hi, Shahar.
Hi.
Nice to see you.
Nice to see you. Yeah, I was wondering, I mean, the situation where the spatial derivatives are, the terms of spatial derivative are subdominant as compared to the temporal derivatives. Kind of reminds a little bit of the post-Newtonian case, but it's the opposite, right? Where there the time derivatives are subdominant with respect to the spatial. So I'm wondering if you can find kind of approximate solutions by expanding order by order in spatial derivatives. Is anything like this?
So once you have like a well-posedness theory, like that basically says the solution exists all the way to the singularity and it's, you know, somewhat under control in this gauge, then absolutely, that's a great question. There is high potential for someone to do some kind of asymptotic expansion. You know, if you want to know what do the different orders of behavior look like, then you know, the theorem gives you permission to start that expansion, and it's gonna be true. Whatever expansion you start, it's gonna be true for a certain amount of time. Whether or not one can justify that expansion for all time, and you know what exactly happens as you head towards the singularity, that's a really interesting open question. And you know, there's a lot of room for work there, and I don't.
But this hasn't been explored.
Not so much, no, because
this has not been explored.
Not well. There wasn't a theorem that says that this. Well, you know, in a crude sense, that is what the BKL ansatz is. You know, it's assuming that the metric looks like this, and then to what extent can you justify that? But you know, the question of how far out in the expansion has been studied. I am not aware of a vast literature on that. I don't think anyone has studied very far out in the expansion. I think basically they did, you know, order zero. You know, suppose the metric looks like this, then to what extent can you justify it? And there are results on the construction of singularities, which is not the same as stability, but just you want to show that a certain kind of singularity exists. There are results that basically assume the first two terms in an expansion and then justify that the third term is an error within a certain subclass of initial conditions. There are such results on that kind of problem. So the results of Anderson and Rendell that I mentioned earlier are kind of in that direction.
Thanks.
Okay. Right. Thanks. We have to wrap it up here. Thanks, Jared, again.
Nice to see everyone.
Another clapping, virtual by many people. Thanks a lot. See everybody next week.
Take care. Thank you.
Bye-bye.